Okay, going back to the experiment we did Friday, we had the cup with the dominoes oscillating at the end of the rubber band, which approximates simple harmonic motion. Only approximates because the rubber band does not do a negative kx. It's kind of close, as long as you don't stretch it too far. Okay, and it turns out that it works pretty well. We use a rubber band just to real quickly assemble. We can get various tensions and so forth using different rubber bands, different lengths. So we use it. Okay, so we do the amplitude, frequency. I asked for the amplitude, frequency, and mass of a cup with 8 dominoes. Now, what people have was a graph of that I asked for, a graph of omega versus number of dominoes. The graph had the appropriate shape, kind of like this. I asked for the mass of a cup with 8 dominoes. Well, turns out that the graph only goes up to 7 dominoes. So we have to kind of sketch the curve and extrapolate a little bit and estimate from this point what omega was. Okay. Now the estimate came out 4.7 radians per second. Of course, I asked for frequency, and the data would have allowed you to do the frequency. You know, you had 2 point some seconds for 4 oscillations or whatever. So that could have been calculated, but yeah, and people did that. Actually, that's not exactly what people did. It was 3 oscillations. They said, you reasoned it out. You reasoned it out correctly. That's 6 pi radians in 2 seconds, okay? And you divide the 6 pi radians by 2 seconds, you get your omega, okay? So, yeah. Omega was pretty well done. I mean, quite well done. So we got this. Now, of course, I asked for frequency, so we got to reason out frequency from omega. Now, my intent was to get the frequency and reason out omega from that, but we see the relationships. So we're going to do relationships between omega and frequency and period. In order to do that, well, the estimate is 4.7 radians per second. How do you represent that on a reference circle? Well, here's your reference circle, 2 pi radians around the circle. And we know that the oscillation corresponds to what one complete cycle corresponds to what circuit around the reference circle. Either projecting on the y-axis to get the sine, or the x-axis to get the cosine, or even in terms of a phase angle. So we'll worry about that later. Let's just take this information and see what we do with it. Well, we say, here's your complete circle, and 4.7 radians. How far is that on the circle? Well, we had a little discussion about that. Is that more or less than a cycle and so forth? Well, where is that in the reference circle? Well, yeah, some people want to say, well, the radius of the reference circle is 4.7 radians. That wasn't a good thought, but you know, we got over that rather quickly. And then ended up with some pretty good results. Okay. So right there's how you picture it. Here's your cycle. I'm sorry, here's your cycle all the way around. Okay, and this would correspond to 2 pi radians. Okay, now 4.7 radians isn't quite 2 pi because 2 pi is about 6, 4.7 is less than that. So 4.7 radians comes around to here. And that then is 1 second worth of oscillation. To get a complete oscillation, you got to go more than a second. Okay? So you can estimate it. Turns out 4.7 radians is very close to 3 pi over 2. Okay, very close to the point down here. Closer than I've drawn it, but I didn't want to draw it. So, okay. 4.71 or so is pretty close, maybe 4.72. Anyhow, there it is. And from this, didn't have any real trouble figuring out what the frequency was. Okay, like if a cycle was here, that would be, it'd take about 2 seconds to get all the way around, right? If a cycle went from here to here, it'd be 4 seconds to get all the way around. Cycle goes from here to here, how long does it take it to get all the way around? Well, in each case, you divide the 2 pi radians in the circle by the number of radians in a cycle. Okay? Just like, write that out. I kind of didn't say that right. 2 pi radians per cycle divided by 4.7 radians per second. Now, what does that give you? That gives you about 1.3 seconds per cycle. I think I might have said that backwards a minute ago. That's 1.3 seconds per cycle, right? So that's how long it takes. Okay. And then 4.7 radians per second is what portion of a cycle? That'll be 4.7 over 2 pi of a cycle. Write it out correctly. Okay. And that comes out approximately 2 significant figures, which is all we're really justified in doing with the data we have. 0.75 cycles per second, which is 0.75 hertz. Now, this is the result you got. Okay. But compare it with this result. Okay. How do these two compare? Well, first place, they're pretty clearly reciprocals. Okay. So why should the frequency be the reciprocal of the period? You want to understand that. Pretty easy to understand in terms of this picture. Okay, this is about 3/4 of the cycle. So your frequency is about 3/4 of the cycle per second. That's 1 second. You go 3/4 of the cycle in a second. How long does it take to get around here? Well, if that's 3/4 of the cycle, it's going to take 4/3 of that long to get all the way around. The fraction is pretty obvious. Okay. And they come at real convenient since you did choose that 4.7 just as an ostensible estimate. So we have the reasoning for the period. Okay. And I emphasize reasoning over formulas because formulas are too hard to keep straight. You got 2 pi and about half a dozen different formulas and things in the numerator, things in the denominator. If you're just thinking symbols, you're not likely to navigate it successfully. Now, if you just think symbols and use the units, you can probably plug your way through it. But understanding the picture is way more secure than pulling out a formula that you don't remember yourself correctly. Okay. Well, in any case, there it is. So now we want the equation of motion. Well, it's going to be, we'll use y equals a sine of omega t. You could have chosen cosine of omega t. You could have thrown a phase angle in there, but I said assume phase angle of 0. Because all we're really interested in is a model of the motion, and we can shift the phase any way we want to. And we'll talk about that. Okay, here's your equation of motion. So y equals 10 centimeters times the sine of omega t. Omega is 4.7 radians per second. Okay. Now, based on this, tell me what your velocity function is. Tell me what your acceleration function is. Okay, now we did have a little brain glitch there. Another word for that, I'll say brain glitch. Taking this derivative, this is a composite. You got to use a change. You don't take the derivative inside here and ignore everything else. So that's going to be 47 centimeters times radians per second. Centimeter of radius times a radian gives you a centimeter of arc. So that's just going to be centimeters per second times the cosine. So 4.7 radians per second times t. And then you multiply by 4.7 again, because when you take the derivative of this, you're going to get 4.7 radians per second. Now, 47 times 50 is, or 47 times 5 is 250 less 15, which is 235. Okay. So I think that's about 235. Now it's going to be centimeters per second times radians per second. Again, a centimeter of radius by times a radian of angle gives you a centimeter of arc. And you want to think that through a little bit more, but that's why a centimeter times a radian can give you a second. Okay. Centimeter divided by radian can also give you a second. Centimeter of arc and divided by radian, you get centimeter of radius. So radian is kind of a phantom unit that comes in and out, but when you multiply it or divide it by length units, you'll pretty much typically get a length unit. Okay, so anyhow, we get this. Is that agreed? So you just nod. Yeah. And it's a negative because derivative cosine is a negative of the sine. And there we have it. Okay. So we don't need formulas. We just know that to get from here to here to here, you're going to take derivatives, and to get from here to here to here, you're going to do intervals, antiderivatives. Very easy to do with these functions. Simple composite of a sine with some linear function, right? Okay. That doesn't mean you shouldn't memorize the formulas, but trust the derivatives before you trust your memory. Okay. If you know the formulas, you can see the derivatives sitting there smiling at you. Okay. It's very obvious. So one more another. Make sure you can do this. Okay, so that's pretty good. So let's answer a couple other questions. What's the maximum velocity? Okay, and also what's the maximum position of wind, and what's the maximum acceleration? Okay, well, first of all, you ought to be able to tell me what the maximum position is, because that's what the amplitude is. Okay. And because they should be negative 10 centimeters. Well, that's exactly the meaning of amplitude. Now, the other questions are a little harder to answer, but you could get the maximum amplitude from the function. Just in general, if you use y equals a sine of omega t, now to write it this way, maximum y is then a times the maximum value of the sine. What's the maximum value of the sine function? Just show me figures of one or two hands. Sine can't be bigger than 1. And circular model tells you that. But it's just something you know about the sine function if you even had pre-calculus, right? And here's maybe the first time you've ever really used it. So, you know, if you didn't think of it, theoretically should have. Well, you do a sine of omega t equals a. So sine of omega t is 1, right? So omega t inverse sine of 1 over 2. You tell that from the circular model. I mean, in the circular model, where is the sine equal to 1? Here. What's theta here? Pi over 2, right? Okay. So the t equals so you divide by omega, you're going to get pi over 2 omega, right? And that's approximately 0.3. Okay, pi over 8.4 radians per second, which is about 0.33 seconds. Okay. So that's how you use the equation. Okay, so if I want to know when the position is 0.7 radians, it's all sine omega t is 0.7, right? Omega t is going to the inverse sine of 0.7, et cetera. You just have to know how to solve those equations. That's pretty easy. You've got to use a calculator a lot of times. And times when I should use a calculator, don't. I just prefer to use my head. And then if I really need a good answer, I'll check it on the computer. If I ever touch a calculator, it's an accident. Or an act of desperation. You get that for every once in a while. Okay, so anyhow, that's how you solve that, right? Okay. So that's how you get maximum position and when. Now, to get the maximum velocity when, maximum acceleration when. Looks like everybody's pretty well on track, I think. For maximum velocity, you have omega A cosine of omega t. Okay. Right. That occurs when omega t is 0 or 2 pi, 4 pi, etc. Now, this is a general answer. This is an answer only in the first cycle. But of course, it repeats then every roughly 4/3 of a second after this. So you can also say that. Think about this. Omega t equals 2n pi, where n is 1, 2, 3, and so forth. It would then be 2n pi over omega, or n times pi over omega. In this case, this. Well, that's algebraic. There's a much easier way to see this. I'm going to go back to the reference circle. Here's our reference circle. Okay. Here's omega t. Call it pieces of chalk. This arrow represents the velocity of a reference point. Okay, we'll call that V ref. There, clicker V ref. Okay. How fast? Pencil's over there. How fast is that point moving on the reference circle? Well, for simple magnitude of V ref equals omega times the radius of the circle. You're talking about motion in the arc of a circle. Definition of a radian. The angle of this vector is omega t plus pi over 2. Direction of v rep. Okay. Also, we have our angular acceleration. I'm sorry, our acceleration. Okay. Moving at a constant speed on the circle, so the acceleration is toward the center. It's a triple acceleration. This is a rep. Okay. And magnitude, hope I get it in here, of a rep is what? V squared over r. V is omega a. So you get omega squared a squared. R is a. So it's omega squared a squared over a, which is omega squared a. In the direction is 180 degrees from omega t, which is omega t plus pi. It'd be great if you could understand this picture, because having understood it, you can tell me, well, there's more to it. So let me just draw it without the label. I have a pretty good circle I drew there. I'll never draw another one that good. Okay. So here we go. I told you I'm not drawing up that good. So using the same colors, I can see various velocity vectors here, 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 just to pick a few points. Those vectors should all be the same length, and I blew that. And our acceleration vectors here, 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 here. Can you visualize how these vectors work as you go around the circle? Okay, well, if you take one of them, let's say we project this vector over to the y-axis because we're modeling the sine function. Okay. This is the actual velocity of the oscillator. This is the velocity of your reference point. Okay. So this is the velocity of the oscillator. Here. Here's the actual acceleration of the oscillator. Now, where will the acceleration of the, where on the circle will we be if the acceleration of the oscillator is as big as it could be? Well, if we're here, the direction of the acceleration is toward the origin. Projection of the acceleration is 0. The acceleration is totally horizontal. It has no vertical component. I could say the projection is the velocity of the oscillator, and that's, of course, the y component of your reference point. That reference velocity. Okay, acceleration of the oscillator is the y component of your A ref. Okay. Now, what direction would A ref have to be in? It has constant magnitude. It's always omega squared A. This is always omega A magnitude. Okay. So the purple vectors always have the same magnitude, the velocity vectors, and the orange vectors always have the same magnitude. So where would what would have to be the direction? Point in the direction of the velocity vector would have the greatest y component. Okay, yeah. The velocity vector is in this direction, the y component is greatest. Okay, so I'll say velocity of the oscillator is maximized at t equals 0, capital T, which is the period, right? In other words, after one cycle, 2t, etc. You know, the t is, so you can write out the sequence, define the sequence of all the times when this thing is maximized. Okay. Now, what's the direction of the, stick with the velocity vector, the reference vector, when the velocity is minimized? Let me ask when the speed is minimized. Okay, this way or this way, right? Good. So that would occur here or here, right? Of course, you know, I mean, if you're tracing the y component as you go around the circle, starting here, it's this, right? And it goes up here and it goes more and more slowly because of the angle of these velocity vectors, because that's the way the sine function works. Okay. So you get here when it stops for an instant and turns back around. And then down here, it does the same thing in the opposite direction. And when's the speed maximized? Well, it'd be either here or here, right? Speed's maximized at capital T over 2, right? 3 times capital T over 2. I'm sorry, yeah, capital T over 2, T, 3T over 2, 3 capital T over 2. Okay, half integer multiples of the period. No. Yeah, that's okay. So, right. Okay. Now I look at the acceleration vector. Where is its vertical component maximized? Here. Well, acceleration vector would be like this, right? Magnitude of the acceleration would be maximized. It would be a acceleration, negative acceleration. And the acceleration is always back toward the center. You can see how these vectors are. And of course, that's the way it has to be because that's where your force is. F equals negative kx. It's always back toward the equilibrium position. And that's totally consistent with this picture. Okay, so you can see pretty much everything in this picture. And you can answer these questions based on the picture. Because now you can say, well, the velocity is maximized. First of all, when this is 1, right? And that would be when omega t is 0, 2 pi, etc. Okay, but that's always at this point. That's where 2 pi is, 4 pi. That's where 0 is. Okay, so totally consistent. You want to think through that. Think through how the equations you get over here match the picture, and understand this picture. Understand how these vectors have. They're always the same, except that this one's always pointing back toward the origin, so it just keeps turning as you move around the circle. Okay. Now I was going to get to energy very quickly. Talked about this last time, but there's energy relationships are very straightforward. Okay, and I guess we can. That's 1/2 m omega squared cosine of omega t. Hey, you got your omega for this particular motion. That's always that. The potential energy. We use y here, so use y in this case. Okay, that's 1/2 k times okay. Now, omega, m, and k are related, aren't they? If you square both sides of this, multiply by m, you see that m omega squared equals k. Which means that this term is 1/2 m omega squared sine squared omega t. As I said last time, and I've left off a in all of these. There it is. Okay. And here. Total energy is 1/2 Ka squared. If I want to know the speed, given that, well, there's a little more work to do. Don't have time to do that right now. I'll try to do an addendum on this. Okay, so you can check it out. Also, looks like my camera wasn't where it needed to be. But this is just repeating what you did previously. Okay, everybody had to leave because we were way over time. But said I'd finish this up. Okay, total energy is 1/2 Ka squared, and that's also equal to, of course, 1/2 mv squared plus 1/2 Kx squared. Because of course that's where the 1/2 Ka squared came from. 1/2 mv squared, 1/2 Ky squared. Let's make that y. Since we're using y, since we're projecting on the vertical axis. And of course, well, I'm not going to worry about that. Okay. So this equation, which you get just by understanding omega is the square root of k over m and using these expressions or these expressions, tells us that if I know total energy, which is either the 1/2 Ka squared, if we know the force constant and the amplitude, then we know the total energy, don't we? Or if we happen to know the maximum velocity and the mass, we could know the total energy. And I've got to adjust the screen here a little so I can make sure we're still in focus. Okay. Focus is behaving pretty well. So the speed at a given position y, well, we just solve this equation for y. And we get so this equation for v, we're given one. Okay. So we have what? We subtract the 1/2 Ky squared from both sides and then multiply, well, by 2 over m. Okay, so we have v squared is going to be 1/2 Ka squared minus 1/2 Ky squared divided by m and multiplied by 2. So your speed is going to be plus or minus the square root of all this. Okay, well, your 1/2 are going to be taken care of. You're going to have Ka squared minus Ky squared. Over m. And of course, then you could factor out the square root of k over m. Okay, but then you recognize that the square root of k over m is just omega. And you want to remember where that comes from. You want to remember the derivation of the differential equation. Okay. And the differential equation, I'll just write it out again. It would be y double prime mass times acceleration, mass times y double prime is net force, which is negative ky. So y double prime equals negative k over m y. So that y equals a would be sine or cosine of omega t plus phi omega is the square root of k over m. And of course, it could be cosine of omega t plus phi. It's a general solution to this equation. You can easily verify it. You can easily understand that the only functions whose second derivatives are negative multiples of themselves are the sine and cosine. Okay. So that's where omega comes from. But you got to remember that. Okay. So we see here, and that this is this. It's a handy formula if you want to memorize a lot of formulas, but it's pretty easy to get to the formula if you just think of what the total energy is. Kind of comes right out. And whether you get that mastered by next week when you have a final exam, maybe you will, and maybe you have to rely on your memory, and good luck with that. But I think you can handle it. Okay, and of course we could also find the position at which you have a given velocity. And solve for y. And we get gotta be careful, I never remember formulas. Okay, just derive it. I pretty much know anyhow, but I derive it to make sure. I don't like to make mistakes, even though I keep making them. Okay, so if we want to solve this for y, we're going to have to subtract 1/2 mv from both sides. And then we'll be dividing by the k, so the k will go out, and we'll have m over k. And yeah, we're going to get it. I don't want to write it down because I have to do some of it in my head, and I probably write it down wrong. But you just jot it out. It's as quick to jot out as this, and then you simplify it. Okay, so there it is. All this is real handy part of your toolkit. So good luck with everything. We are going to meet for a while on Friday. Hopefully we'll be able to clarify some things. If you have questions you want me to address, situations that you're having trouble with, email me. I'll do my best to get you some videos. Or otherwise answer your questions. Sometimes I can answer them just typing out a couple of sentences. Okay. And also, one other thing, we'll have office hours next week. I haven't set them yet, but they're going to be probably around the same hours as the lab period. Okay, give or take a little bit, kind of midday, late morning, early afternoon, about 3 hours each day. Okay. Monday, Tuesday, and Wednesday of the exam week. None on Thursday or Friday. Because I got to get into grading and recording grades and stuff. It's getting late. Okay, so take that for what it's worth.